Rồi, sau cái giáo sư phải có một cái gì hay nói người
Distinguished guests, ladies and gentlemen, boys and girls, welcome to the 5th Annual Conference on Science Research in English 2013. First of all, may I introduce myself? I'm Nguyễn Phương. I'm from English and Social Study Department. Belong to the high school for students, Hanoi University of Science. And today I will be the MC for the conference. And please give me a big hand to begin with the conference. I would like to invite distinguished guests, boys and girls, and ladies and gentlemen, boys and girls, to enjoy some performance by the students in High School for Gifted Students in Science. Please welcome.
Our winners have 5 students from my class who are Bùi Di Anh, Nguyễn Việt Dũng, Đặng Thu Hằng, Nguyễn Nguyên Hoàng, and Hoàng Lê Đình Tùng. And the supervisor is Master of Science, Mr. Bùi Công Huấn. According to our group opinions, it is true that for a long time the simultaneous equations have played an important part in experimentation. And I will introduce some problem of this. There are also our research purpose. You can see there are 3 purposes. One, solutions properties and theory simultaneous equations, which have one equation can be factorized into factor. 2, general solutions properties and simultaneous equations by factorizing the polynomial factor. And 3, how to solve a simultaneous equation when we know 2 roots of each. Okay, please look at the headline. Our results have 2 main points. The first one is using Casio calculator to solve the simultaneous equations. And the second main point is the method of undetermined coefficients is solving some symptoms of simultaneous equations. Okay, let's start with part A. Run quadratic simultaneous equations. You can see the solutions have 4 steps. Step 1. Give the variable some values. Step 2. Factorize the polynomial into factor and identify. Step 3. Determine the relation history to variable. And step 4. Replace and solve the equations of one unknown. It's quite easy, so we move the bus to cubic simultaneous equations. The methodology X and X is equal 1. So, please give us an example. First, we suspect that 1 can be analyzed as a factor, so we have the solution. Like the methodology, the solution has 4 steps. Step 1, give the variable some values. Step 2, factorize the polynomial into factor and identify. Step 3, determine the relation between two variables. And step 4, replace and solve the equations of one variable. And in this part, we have only a remark. After giving the variables a value, if the equations of another unknown doesn't have roots in R set, that means the first equation is the same can be factorized into factor. Now we continue with part B. The method of analytical coefficient is showing some symptoms of simultaneous equations. One quadratic simultaneous equation. Here is the original form of it, and the problem is how to find a real number k. So that k multiplied to 2, then add together with 1 become a decomposable polynomial. It is a difficult for you. Don't worry, it's the solution. It seems quite complicated, but I think not difficult for us about polar mathematics. And after all of this, we have k in the root of the equations. And with the help of natural calculator, we can find values of k. Let's use this methodology to solve the example. You can see, example has 3 steps. Step 1, find k. Step 2. Step 2. Determine the relations between two variables by factorizing the polynomial into factor. And step 3. Replace and solve the equations of one unknown. Now we move back to higher degrees of simultaneous equations of two unknown. Problem. We still use the methodology to find k, like the past one, but in this case, we have some difficulty. K now is not only a real number, but also a polynomial variable. And if we know the root of it, we can find k easily by the methodology. It has 3 steps. Step 1, trace to root of the system. Step 2, identify the stress line passing through root point and express another unknown by another and replace an A, B. When we have a comma, B comma, now k equals a comma divided comma minus. Let's use this methodology to solve the equation. Right here, the solution has 3 steps. Step 1, find k. Step 2, determine the relationship between two variables by factorizing the polynomial factor. And step 3, replace and solve 2 new systems. The first one is easily solved by replacing, and the second, we use the methodology as one to solve it. And in part B, we have a remark to the second type of symmetric is special case of the methodology when k is equal to 1 minus. Okay, conclusions. I have told you about our research report. As I told class, it would be helpful to you. Now I really want to give special thanks to Master of Science, Mr. Nguồn, Mr. Nguyễn, Associate Professor Dr. Nguyễn, who helped us very much with this research and make it better. In the end, thank you very much for being attention to my talk.
Thank you, Nguồn. Well done. Your English is so funny and make people surprised with your English. And next, we'd like to invite the group one who will present the coloring techniques in a table. By Nguyễn Đức, by Hoàng Minh, by Đặng Hoàng Hiệp, by Nguyễn Xuân Dũng, Supervisor Miss Master of Science, Nguyễn Thị Thùy Linh.
Hi everybody, my name is Đặng here, and today we'll talk about the coloring technique in table. We'll have for the Nguyễn Đức, Minh, me, and our supervisor. Our presentation has 4 parts. Introduction, example, some problem with the Olympiad examples, and some problem expand. Now we come to the first part, examples. Here we have the first example. Sorry, come to the introduction. So we have combinatorial problem by using coloring techniques, and we will pigeonhole principle. Coming to the example 1. On the F times H chessboard, there is color square. This one square, which is necessary color. Find the minimum number of color square. So the minimum number of color square is 20. Example 2. In an S times S chessboard, S times S chessboard is colored by K color. So that X square is colored with one color, and there are at least 2 squares that next to it are colored with the same color. By the maximum value of K. Here's the solution. First, we color alternately so that when you color the yellow square, then next to it 2 white square is colored. So that, and when the white square is colored, 2 yellow square next to it is colored. So in the 2 times 2 square, we have 4 square colored by 1 color. So we can color in the following figure. And the maximum number of color square is 16. Now we talk about the problem in the Olympiad exam. Here we have example in Ibero-American Mathematics Olympiad 2004. This is given 2001 times 2001 block divided into 1 times 1 square. We want to mark f square in such a way that first these 2 squares are adjacent, then one of them is marked. Each 2 squares lie consecutively in a row or column. Then 2 adjacent squares from them are marked. The minimum number of squares we most mark. First, we solve that any 5 consecutive squares in a row or column. At least 3 are marked. Case 1, 2 consecutive squares in the block of 5 is marked. So at least 2 of the other 3 are marked. So we will talk about this. Case 2, there's no 2 consecutive squares in the block are marked, so the marking form then the marking from 1 is 2 pattern. Here in the first pattern, we will have 3 color square, so we don't talk about this. And in the N2 pattern, we have 2 color square. Now let's put it in the 6 and put it 3 block in the 6 block. Then the remaining square, if whether the remaining square is marked or not, there's no adjacent square to it marked, so it will break the rule. So making it quite possible. Now we can divide table into 5 times 1 or 1 times 5 block by dividing table into 2001 times 2000, 2000 times 1 and 1 times 1. And the squares be represented by other pairs with integers m and with 0 smaller or equal m smaller than or equal to 2000, 1000. Mark m is m plus n when divided into 5 remain 1, 3 or 4. To count the number of marked square, we divide all but the square 0, 0 into not overlapping 5 times 1 times 5 block. It's small block and 3 marked square, so the minimum number square, marked square is 600 and 1200. In conclusion, when using coloring techniques, we partition the figure, then we consider its path to color. Now we have some problems explained. Lesson 1 is given a 2n times 2n in color by trace color, so that x square is colored by the color, and in the adjacent cell, common side has at least 2 boxes the same color with it, hiding the maximum value k. First color alternatively, so that mix color yellow square by red, then mix with 2 white square must be colored by red. So we have at least 4 square color by 1 color. So we can color X in the following figures. And the maximum number is 2n square. We can end here. Thanks for listening. Thank you very much.
Now I would like to invite the group 3. Using your presentation is using invariant to solve combination problems. Presented by Phạm Tuấn Minh Tú, Ngô Quang Dương, Nguyễn Hoàng Giang, Lương Triều Dương, Lê Tuấn Phong, and the supervisor is the Master of Science, Bùi Thị Quyết. Please come to the stage, please.
I am Phạm Tuấn Minh Tú, and today we introduce our subject report. Our group have 5 members, me, Nguyễn Hoàng Giang, Ngô Quang Dương, Lương Triều Dương, and Lê Tuấn Phong, and our supervisor is Mc Bùi Thị Tuyết. We have 4 times. First, introduction, the second, sample, the third, problem and solution, and the last is reference. First, introduction. Invariant principle. Seek what's below the G9 or invariant. Each has no challenge, so practice is the only way to good at spotting. In this project, we will show you some common sample, complex problem, and invariance in Metro-API. Let's start with sample 1. This is a VMO 1992 problem, and the question here is, can we paint on the board by this way? And this is the solution of that problem. We write a natural number on the board, so we will find the real sum is 3k, so we cannot paint on the board by this way. And this is a sample to by area 1999 problem. And we have to find the way to open the up by switching the number. I replace the number by 1 or minus 1. So if I want to change 1 minus to 1, I press on the key on the same column or row within so it may be changed 4 or 2 times, but 1 minus change 7 times, so we can open the number 1. The third is problem and solution. This is a general case sample 2 with 4 times M and keys. So the question and the solution in line the sample 2. We have a box like that with 2M multiplied 2M. If I want to change key K to K minus, I press on the key on the same column or row of this. So L on M change to M times, plus L change to 2 times, so we can open the lock. And we refer this documentary, so I want to give thank you for my project. And this is all my report. Thank you very much for listening. Thank you.
Hello everybody, my name is Tuấn Anh and today I would like to present about how we use past in 3 Cartesian integer coordinate system and to prove combinatorial identities. My group consists of Lê Thành Nam, Phạm Công Sơn, Nguyễn Tuấn Anh, Nguyễn Đức Minh, Đặng Thị Yến Anh, Kiều Thị Thu Hà, and our supervisor is Associated Professor Dr. Nguyễn Vũ Lương. Now I would like to begin. First, I would like to introduce some basic principles. We call an equal path in a 3 Cartesian coordinate system from A to B. With these coordinates are a sequence of moves that goes along the line X, Y, and Z. There are some basic principles that the number of paths from A to B is C M, M plus B multiplied by C N plus B. And if we translate these coordinates to C with these coordinates and B with these coordinates, we obtain the amount of what from C to D is this amount. Okay, keeping that in mind, we arrive at the first equality. Now, as we see in the right hand side, it is the number of ways to go from A to B. So we would like to count it in a different way to arrive at the right hand side of the identity. Now, we know that any wave that goes from A to B must pass through at least 1 point in the plane x equal to m minus 1. So we can assume that S is the last point that we travel in this plane. And because S is the last point that we travel in this plane, then after S we must move to a point T that has the coordinates n, I, and k. And so S can be variable in all these planes. And so the number of ways to go from A to B is equal to the number of ways to go from A to a point on this plane, and multiplied by the number of ways to go from that point to B, which is C n minus 1 m plus I plus k subtract by 1 multiplied by c I plus k multiplied by c and minus I and m plus p minus I minus k. And so we complete our solution. Now we arrive at the second identity. Now let us analyze this case. In the right hand side, it is the number of what that goes from the point A1 with the coordinates minus 1, 1, 0 to B. Now we would like to count the number of blocks in a different way to arrive at the left hand side. Now any blocks that goes from A1 to B must pass through at least one point on the plane EF, TS with the coordinate x equal to y minus 1. Now we denote R is the last point on that plane that we pass through. So we count that the way that goes from A to B is similar to a way that goes from A1 that pass through K, pass through R, and from R go to B. And the number of ways that we go from A1 to R is equal to the number of ways that we go from A000 to R, because A1 and A is symmetric with respect to this plane, and the number of ways that go from R to B is can be easily calculated by the first basic principle. And so we arrive at the left hand side, and that proves our identity. Now we have some consequence of the theorem. We call that what from A to B is a what that intersects the THPT that we introduced earlier, and denote the F, M, and Q that the number of good blocks, which means the blocks that are not bad blocks. And according to the last theorem, we can easily calculate the number of good blocks is this amount. And keeping that in mind, we arrive at the theorem 3. Now, as we see in the right hand side, it is the number of what that is the good what that goes from O000 to M, and Q. So we would like to calculate the number of watts in another way to arrive at the left hand side. Okay. When starting from O, in order to have a good watt to M and Q, we must pass through the point A 100 or B 001, because we put a pass through the point S because it belongs to the plane EF, TS, which we wouldn't want to pass through. Now we calculate the number of ways, good ways from A to M. Now, as we see, any good ways that goes from A to M must pass through at least one point of the plane x equal to y. That is in the figure is the plane O, M, P. Now we denote TS is the RS is the first point that we passes through in this plane. In order to pass through RS, we must pass through TS with these coordinates, because RS is the first way that our watts intersect with the plane O, M, and P. And so the number of good watts from O to M is equal to the number of good watts from O to TS, and multiplied by the number of good watts from RS to M. And by our results, which I showed earlier, we can easily calculate that it is exactly equal to the left-hand side. and it can be obtained by another by some simple evaluation here too. That is all I would like to present. Thank you all for listening.
Thank you, Mr. Green and your teammates, for your encouraging and your work is so great, incredible, so clearly. And now, next, I would like to invite the group number 5. You will present applications of unorthogonal problems related to the silent life, presented by Nguyễn Thế Hoan, Vũ Tiến Sinh, Nguyễn Văn Linh, Đặng Đình Khánh, Phạm Lê Việt Đức, and the supervisor is Master of Science, Trần Quang Hùng. Please welcome to the stage and thank you.
Hello everybody, welcome to our group presentation. We are a group of 5 students who are Vũ Tiến Sinh, Nguyễn Thế Hoàn, Nguyễn Tuấn Linh, Đặng Đình Khánh and Phạm Lê Việt Đức. Our supervisor is teacher Trần Quang Hùng. Today we're gonna show you some application of an orthogonal problem and the Simpson line. First, we're going to talk about a basic problem. We will expand. Let ABC be a triangle inscribed in a circle O. A changing line L always pass through a fixed point P on the circle. Through ABC, draw lines perpendicular to L. This line intersects L at A prime, B prime, and C prime. Prove that first, lines pass through A prime, B prime, and C prime and perpendicular to BC, CA, AB respectively are congruent at point Q. Point Q belongs to the fixed line when the lines L change but always pass at point P. From this problem, we got an important result. Let ABC be a triangle inscribed in a circle O. A line L intersects the circle at 2 points M and N. Prove that the orthogonal center of the line L with respect to triangle ABC is the intersection of the Simpson lines of point M and N with respect to triangle ABC. And we're going to talk about an application of the above result. It's a concurrent Simpson lines problem. Let ABC be a triangle which is inscribed in a circle O. The lines that pass through ABC and parallel to the opposite side cut the circle at D, E, and F. Then the Simpson lines at point D, E, and F with respect to triangle ABC concur at point P. The Simpson lines at point ABC with respect to triangle D, E, F concur at point P. Next, we're going to talk about the fixed problem, which is related to Taylor's circle. Now, let us show you an interesting problem about the Simpson lines. Let ABC be a triangle which is inscribed in the circle O. Line L cuts circle at point M and N. Let P be two arbitrary points on segment M and N. We note omega P and omega Q be the Taylor circle of P and Q with respect to triangle ABC. Prove that while P and Q change on M and N on segment M and N, the radical axis of omega P and omega Q always pass through a fixed point. Next we're going to talk about an interesting problem we discovered. Let ABC be a triangle inscribed in a circle O, and D, E, and F be points on arc B, C, C, A, B that do not contain ABC. The Simpson lines of D, E, and F with respect to triangle ABC form triangle B prime, E prime, F prime. The Simpson lines of ABC with respect to triangle D and F form triangle A prime, B prime, C prime. Prove that 6 point B prime, E prime, F prime, A prime, B prime, and C prime are cyclic. To solve these problems, we need some well-known lemmas. Lemma 1, let ABC be a triangle with orthocenter H. Prove that the Simpson line of point P passes to the midpoint of PH. Lemma 2, the angle formed by Simpson lines of B and E with respect to triangle ABC equals to half arc EE. Lemma 3, given triangle ABC, point D, E, F are on BC, CA, AB respectively. Let O be the intersection of circle A, AF, BF, B, C, D, E. Prove that O is the orthocenter of triangle EF if and only if O is the circumcenter of triangle ABC. And finally, number 4, given triangles ABC and DEF inscribed in the circle O, let MJN be the Simpson line of A with respect to triangle EF, and PQT in the Simpson line of D with respect to triangle ABC. Prove that the angle formed by BC and NJN and EF and PQT are equal. Next, we're going to talk about the widening Simpson line. Given triangle ABC, P is the point on the circle triangle. X, Y, Z are 3 points on BC, C, AB, and group points P, X, Y, C, and P, X, Z, E are concentric. Then we have X, Y, Z are collinear. And let alpha be the acute angle formed by PX and BC. Then XYZ is the Simpson line angle alpha point P with respect to triangle ABC. We next want to talk about the one 6-point problem. Given triangle ABC is cut in the circle O, D, E, and F are on the axis BC, CA, AB respectively. D prime is the orthogonal center angle alpha lines EF with respect to triangle ABC. Similarly, we have E prime and F prime. Let A prime is the orthogonal center angle alpha with respect to triangle EF. Similarly, we have B prime and C prime. Prove that 6 point A prime, E prime, C prime, E prime, and F prime are concentric. Finally, we cover a beautiful and very amazing problem. Given pentagon A, B, C, D, E inscribed in a circle O, consider 10 points which each point is the intersection of the Simpson lines of 2 random points. With respect to the triangle which is built by the rest 3 points, then this 10 points are concentric. This is the end of our presentation. Thank you all for listening. Before we finish our presentation, we would like to thank the teachers in Nguồn, our supervisor, for helping us finish our research.
Thank you very much for the good fight, for your persistent work. Yeah, and Bata, yeah, please. Please, I would like to invite Group 6. You will present the porcupine theorem, presented by Phạm Thị Oanh, Trần Thị Thu, Vũ Thị Ninh, Trương Mai Ngọc, and Mai Thị Thu Lý. Supervisor, Master of Science, Nguyễn Tiến Lâm, please.
Hello everybody. Let me introduce my groups. We have 5 students come from our class, 10A to math class, and our advisor is Mr. Nguyễn Tiến Lâm. Our topic is porcupine theorem. It's a famous theorem in geometry, and we use it in space geometry. And in this topic, we do it with a theta theorem. Let's I1 and 2 and 3 and 4 be a theta theorem, and AI is a unit vector which is perpendicular to the base of the symmetric AI. SI is the area to face AS, AK, AI, and alpha AJ. Alpha IJ is the measure of the dihedral angle formed to face opposite to the peptide AI, AJ. And HJK is from the set 1, 2, 3, 4. And we have a theorem 1. You can find this equality in many books, and it can be grouped in many ways. You can use volumes and many other ways, and this theorem is very useful to group some following results. We build some following results ourselves. Corollary 2 and corollary 3. Corollary 2 is a cosine rule for tetrahedrons. It's similar to the cosine rules for a triangle. This ISKL is a permutation of 1, 2, 3, 4. And we group it by theorem 1. We have this equality and squaring it directly both two sides of the above equalities. And no subtraction, and the group is complete. And from corollary 2, you will have four equalities, and with four equalities, you add all the equalities, and you will have a corollary 3. And we have some results. Theorem 4 is theorem for the orthogonal projections. And from theorem 4, we have corollary 5. It's called tetrahedrons and equality, and corollary 6. I'll give you a minute to read the proof for the theorem 4. Okay, next step. And the proof for corollary 6. It's easy to understand. Okay. And finally, we have a problem for you. Suppose that zeta is a sphere with center I. The radius r is prime in the tetrahedrons A1, A2, A3, A4. Zeta is a tangent to the face opposite to the peptide A1, A2, A3, A4, and B1, B2, B3, B4, respectively. Products among the angle formed by a pair of distinct rays, AB1, AB2, AB3, AB4. There exists an angle phi with cos phi greater than or equal to -1/3. This problem is not very difficult. I'll give you a small hint. You must use Porcupine theorems and some judgments, so you will easily get the correct answer. Okay, our topic is finished. Thanks for listening, and I hope that our topic will be helpful for you. And I give a special thanks to Mr. Nguyen. Thank you for his help, and this is our result. Thank you.
Thank you very much. It's so lovely to your presentation and your English. Yes. And now we would like to invite Group 7. It will present about the well-known inequality in triangle. Presented by Tạ Hào Nguyễn, Ngô Chí Dũng, Trần Xuân Đạt, Nguyễn Mạnh Hùng. Supervisors by Master of Science Nguyễn Việt Hùng. Yeah, please.
Good afternoon, everybody. My name is Tạ Hào Nguyễn. Our group is 7. Today, in my presentation, I will introduce to you about some well-known inequalities in triangle. And first, I will introduce to you our group. Our group members are Tạ Hào Nguyễn, Hồ Chí Dũng, Trần Xuân Đạt, Nguyễn Mạnh Hùng, and our supervisor is the Master of Science, Nguyễn Việt Hùng. To begin with, let's consider two well-known inequalities having concern in a lot of documents in mathematics, which is taught on the class, where ABC are the three angles of a triangle and x, y, z are real numbers. And you can see these are the two equivalent forms of real numbers and 3D. And there are two proofs for this. For the first one, I will introduce to you now. And the first one is vector method. Let I use the in-center of a triangle ABC and x, y, z and perpendicular height of eyes to the side BC, AB. And by developing the obvious inequality, the square of x multiplied vector Ix plus y multiplied vector Iy plus z multiplied vector Iz is greater than or equal to 0. And after some few steps, we can easily derive our design inequality. And the equality occurs if and only if x over a equal to I over y over b is equal to z over c. And the second method we will reduce the inequality to another form. As you will see, the inequality occurs if and only if x over CA equal to y over CB equal to z over CC. Now, just have a look on a triangle with three angles: b plus c over 2, c plus a over 2, a plus b over 2, and update the second inequality. Now let's move on to some result and extension. The first is the problem 1. Prove that for ABC greater than 0, we overcap. The idea we can reduce the above inequality to another form. And from now on, the inequality that the inequality which is located in the red box in the main or the core inequality to solve our design inequality. And in the boxes inequality, if we replace x, y, z by square root of a, square root of b, square root of c, and we can easily get the proof. Now move on to a very well-known inequality, that is 4D curve inequality. And the idea after a few steps we can easily derive the inequality. And these two because we have used the red box again, and but not for the three variable x, y, z, but for the three variable a power 2, b power 2, and c power 2, and now we move on to the last problem, which is very useful result. Prove that for two triangles ABC, A1, B1, because we always have the inequality. And you will see that if we don't know the four previous inequalities that I have shown you at the beginning of this report, we cannot solve this inequality easily. because we will need some time and we cannot overcome it easily. And the idea, if we consider the triangle A prime, B prime, C prime, and we make a transformation x, y, z by C A prime, C B prime, C prime in the red box in equality. But we haven't done without the notice that C A prime over C B prime C C prime is equal to cos B prime plus cos C prime, and similarly we have two another equalities. And now from three notices I give you, we can easily derive the inequality sign. Now let us spend. Now I suggest you to spend a little increase your time to have a look on our summary to see that how much we have done in with, and remember that with just for inequality, basic inequality I have shown you in the other beginning of our report, and you will create some inequality. So we have created for about approximately 12 inequalities, and in our conclusion, I would like to give my special honest thanks to Master of Science and other teachers in high school for the students. The mathematics department, and I would like to thank everyone to pay attention to our presentation, and I would like to wish you health and happiness.
Thank you, Group 7, for your clear and creative work, and hopefully we will have a better problems and study in the future. And now I would like to invite Group H. You will present the application of the creating sequence in some arithmetic sequence problems, presented by Nguyễn Minh Tú, Nguyễn Việt Duy, Nguyễn Tuấn Anh, Nguyễn Viết Di, Nguyễn Tuấn Anh, Đỗ Tấn Mạnh, Vũ Kiều Minh Anh, supervised by Master of Science Vũ Hải Sơn.
Good afternoon, teachers and students.
We are presenting to you the explorations and creativity research.
We are Group 3 for 1101 Mathematics, and with the help of Supervisor Vũ Hải Sơn. And our presenter today is me, Nguyễn Viết Duy, and
me, Vũ Kiều Minh Anh. We are doing all the research on the applications of creating sequences in some arithmetic sequences problems. Let's begin with the first problem. The segment xn is defined by
x0 equal to 0, x1 equal to 45, and xn plus 1 equal to 3 times xn minus 1, with all n not more than 1. The mission is that we have to find a small such that 2012 as 2008 minus k, which is a non-negative integer. Let's look through the solution for this problem.
so with this question, we have to consider about the divisibility between each term of this sequence. So with this problem, we can easily see that 2008 minus 8 divisible by 4. So it's decrease the difficulty of this problem. However, the characteristic equation of this sequence has to look like this. So you can see that it may not helpful for a number theory problem. So we have to create a new sequence, and let's suppose yn satisfy that yn minus xn divisible by 503 with so you can easily see that the characteristic equation of yn is like this. So it's not difficult to see that t equal 1 is the best one for this problem.
Alright, let's move on to the next problem. Based on the idea of the first problem, we have created our own problem. Let's take a look at it. The sequence xn is divided by xn equal to 7, x2, x1 equal to 7, x2 equal to 50, and xn plus 2 equal to 4 times xn plus 1 plus 5 times xn minus 1975. The problem requires to prove that 1997 is a divisor of 1996. Let's take a quick look at the solution for this problem. Finally, I want to discuss with you the third problem. Let the sequence an divided by a1 equal to 3, a2 equal to 11, an plus 2 equal to 4 times an plus 1 minus an with natural number n. The mission is that we have to prove that for every non-negative integer n is the sum of 3 perfect squares. Here is the solution. We will spend a few seconds on this solution.
So you can see that with this kind of special question, we have to try some small values such as a1, a2. So we will have to get the expression of the sequence that is the sum of 3 perfect square, and enter the two sequences like this. So we can easily to divide the two sequences un and bn like up of this slide. So you can see that it's not difficult to use the mathematics induction. We can improve that an equal un square plus 2 times bn square with every n greater than 1. So to sum up our presentation, we have some recommendation to you in solving sequences. So the most common first attempt is calculating some small values, example 1 or 2, which helps us a lot to find out the rule of the sequence.
This is the end of our presentation. Thanks for listening.
Thank you for your amazing work, and I would like to invite Group 9. You will present the solving functional equations by some methods. Presented by Tuấn Anh, Nguyễn Duy Khánh, Nguyễn Đức Mạnh, Nguyễn Hoàng Minh, Vũ Trường Sơn. Supervisors by Dr. Please.
Hello everybody, welcome to the presentations of our group. There's 5 people in our group, and here is our names. We come from class 11A through Math, and our supervisor is Dr. Phạm Văn Quốc. Today, I'll give you a talk on functional equations. This is an interesting topic. It appears regularly in mathematics contest of Vietnam and international. We have to have various knowledge and skills to solve it. And here we provide 4 methods. They are considering values, acting variable, undetermined factor and periodic function. The first one is considering values. This is the basis method. In this method, we considering some special values such as f-1, f0, and f1 to find the special properties. And all the choice must be inherited. And here is the example. This is in VMO 1995. Okay, that's all it is. Let's x equal y equals 0. We have f0 equals 0 or f0 equals 1. If f0 equals 0, we have fx equals x is the result. If f0 equals 1, let x equals 0, we have the result is fy equals y plus 1 is the result. We have satisfying the result. Okay, it's very easy. Next, the second one is adding variable. Adding a new variable and calculating the new expressions in two ways, then we will have the result. Okay, this is the example. And really the first thing we have to do is add a new variable that's greater than 1. So we have the result that we have the result that fx dash fxy equals dash fy. And giving z equal 1, x equal y equal 1, x equal 1, and x greater than y greater than 1 in turn, we have the result is fx equal x with all x from 1 to with 1 to individual proceeds. And now we come to the next method. It is undetermined method. I think that it is a useful method. We have to do 3 steps in this. Step 1, based on the initial conditions to determine the form of axis. In general, it's mainly fx equal ax plus b or fx equal a squared x plus bx plus c. Step 2, equal the factors. Step 3, demonstrate the result is unique. Here is an example. Based on that, x dash 1 minus x dash squared x and dash so we have a dash fx by equal to equal the factor. We have fx equal 1 squared x plus 2x minus 1. And suppose that G is different from fx, such as satisfy the initial conditions, we will have the result fx equal 1 plus x. We will have the result fx equal 1 equal squared x plus 2x minus 1 is a unique result. And the last one is the periodic function. In this part, we have some theoretic definitions, fundamental properties, useful numbers. and this year. And now is zero. This is in IRO Summit 1996. We give thus fx plus a plus b minus fx plus a equal fx plus b minus fb, where a is equal 1 by 6 and b is equal 1 by 7. Summing up these equations for x plus b into a plus 6b, we obtain fx plus a plus 1 minus fx plus a equal fx equal x plus 1 minus fx. Summing up the new equations for fx, f plus a for x plus x to x plus 5x, we obtain thus f x plus 2 minus fx plus 1 equals f x plus 1 minus fx. And followed by induction, and followed by this induction, we have the result that the form of fx is fx plus 1 equal fx with all x is r. Okay, I have finished my presentation. Thank you, Dr. Phạm for supporting, and thank everybody for listening.
Thank you, Group 9, for encouraging words. And now I would like to invite Group 10. You will present your topic is configurations in solving combinatorial problems. Presented by Nguyễn Tuấn Anh, Phạm Tiến Đạt, Phạm Vũ Minh Thường, Nguyễn Thị Lê Giang, Nguyễn Nhật Minh, Trương Huy Đức, and Supervisor Master of Science, Phạm Văn Hùng.
Hello everyone. In many competitions like the VMO, the VNST, or the IMO, combinatorial problems play an important part. We can see that finding the configurations in these problems are the key in these international and local competitions. This method has been used widely as in the IMO 2013, problem number 2. Therefore, we students in 10A1 IT wrote this paper to propose ideas and experience of this method. It is possible to say that the main idea of this method is to change our approach to the problem to another way, another viewpoint with similar characteristics, but with it we can solve the problem easier. The participants in our group include Nguyễn Tuấn Anh, Nguyễn Thị Lê Giang, Trương Huy Đức, Nguyễn Nhật Minh, Phạm Tiến Đạt, Phạm Vũ Minh Cương, and our supervisor is Mr. Phạm Văn Hùng. Now we move on to some model problems. We'll begin with some simple examples. Example number 1. How many ways are there to divide set S with n elements into two subsets, including empty sets, so that the set of them equals S? Here's the solution. We see that the problem here is pretty general, and the ideas of counting by retrieval proven by the inductive methods appear at the beginning of the example. Although if we draw a model, as you can see here, this problem will become clearer. We can represent two sets, A and B. Above all, we have to do is apply each element with X belonging to S and put them into the circles. We have 4 ways to arrange them. The first is, but as you can see, we can't count case number 4. but the problem requires a set of two subsets. But the problem requires a set of two subsets to equal S. So we can count case number 4, which therefore with each element we have exactly 3 ways to arrange them, hence the answer here. Now we'll move on to the second problem. Given a positive integer n, T is a set that includes positive integers. How many subsets S of T has the property in S? There's the OAB, so that the absolute value of A minus B belong in the range from 1 to n. We can see that constructing a formula in a 2 by n table like above is the only plan of attack against this problem. But the terms here require us to construct multiple retrieval formulas to solve the problem. Here's the solution. We see that Sn is the number of ways to fill the board in the problem. With x by n plus 1 rectangle with the dominoes covering the square n, there are three cases. Square n and 2n is filled. Square n plus 1 and 2n is filled, and square n and n plus 1 is filled. We can easily derive to the following equality, and inductively we have S2k equals F2k, and S2k plus 1 equals F2k plus 1, with Fn as the nth Fibonacci number. And we arrive at this equality. Now we'll move on to the next problem. We have 200 students competing in a math competition with 6 problems. We know that each problem is solved by 120 students. Prove that there are 2 students so that each problem is solved by one of these 2. Here we have a solution. Examining a table with 6 rows, each row representing a student. We write in the number 1 if the corresponding student can't solve the corresponding problem. Write in the number 0 for any other cases. And call T the set of numbers 1 in the same row, and we can count T in 2 ways. We have way number 1, which is counting by the columns. The elements of T in each pair of columns, they are 200C2 pairs in the columns. So we arrive at the following inequality with the absolute value of T being larger than or equal to 200C2. And we have way number 2, counting by the rows. Each row contains at most 80C2 pair of 1s. There are 6 rows, so we have the following inequality, as you can see. From 1 and 2, we arrive at the inequality. As you can see, the equality above is impossible. So as you can see, we have completed the problem. But we have a notice here that with function fn equals nc2, we have n multiplied by n minus 1 divided by 2 is a convex function. And according to the Jensen inequality, we have the following inequality. We use the inequality you can see there with the following property. Then we move on to our final problem. A set containing 4,027 points in a plane called Columbia. If the 3 points are aligned at the same time, there are 2,013 points that are red and 2,013 14 points that are green. The planes are divided into different domains when we draw out a few segments. One way of drawing out these segments is called the good way, if it satisfies both of the following terms. No segment passes a point in that set. No domain contains a green and a red point. Finally, so that the Columbia set containing 4,027 points, there exists one way to draw K segments in a good way. Here's the solution. We'll be proving that with n red points and n plus 1 green points, that mean K equals n. Step 1, we are proving K is larger than or equals n. If we examine the structure of the circle with n red points and n plus 1 green points, arranged in an alternating way, as shown below, a line that passes through the space between a red and green point is a good line. We can easily see that a good line only passes through at most 2 empty spaces. So the smallest number of good lines is, as you can see. Step 2, we build a set of n red points and n plus 1 green points. Then there only exists a primary of 2n plus 1 divided by 2, which equals n lines that divide the planes into lines. As you can see, n equals 1 is the correct answer. Assuming that with every k smaller than n, we prove that it is correct to n. D is the number of domains of planes that contain points with different colors, and we can draw a convex hull of 2n plus 1 given points. After examining apex A and a line that passes through A and the distance from the other points to AB, we can examine a line that passes through A as D minus 1. If we choose A as the rotary, we can examine a different line called M and its distance to other points. D is always, as you can see, E is always decreasing because D is an infinite range of positive integers. So there only exists one point in time where D equals 0. If AB has different colors, then we examine C, an apex adjacent to and has the same color as A or B. Assuming that C is adjacent to and has the same color as A, we again choose the same rotary as above with the line AC. There always exists a way to divide so that the points with another color. We have n red points will be divided by a primary of n divided by 2 lines, and n plus 1 green points will be divided by n plus 1 divided by 2 lines, the sum of which equals n. So this is the end of my presentation. As you can see in my paper, I will state some example problems and some references. I hope you enjoyed, and thank you for listening.
Thank you very much for Group 10 for your sophisticated work and your excellent English. Is that right, everybody? Is that right?
Yes.
Yes. Okay. Now, I would like to invite the Group 11. Your presentation is application of vectors improving the alignment of tree. Presented by Nguyễn Tiến Khải, Nguyễn Thọ Khang, Trịnh Thị Thùy Linh, Nguyễn Huy Tuyển, and Nguyễn Đức Anh. Supervisor by Master of Science Lê Thị Việt Anh.
Ladies and gentlemen, my name is Nguyễn Thọ Khang. Only welcome to the presentation of our scientific research topic, application of vector improving the alignment of tree. First of all, on behalf of our group, I would like to say many thanks to our supervisor, Master of Science Lê Thị Việt Anh, and our mathematics teacher, Associate Professor Dr. Nguyễn Hữu Lương.
Master of Science Hải Sâm and Master of Science Trần Quang Hùng for giving us a lot of support and help on working on this project. And now is the content of the topic. Nowadays, the method of grouping Nowadays, the method of using vectors to group reports aligned is used in many national and international competitions. Furthermore, since vector has many applications, a good and unique solution for those societies is not always available. In this topic, we will present some application of vector in geometry to group the alignment of 3 points. The topic includes 2 parts. Part 1, general method. In this part, we will introduce two methods to group the alignment of 3 points using vector and using a power of a point with respect to the circle. And part 2 is exercises and application. Now we get to part 1. With the method 1 is vector to group collinearity. Let's start with a basic theorem. 3 points A, B, C are collinear if and only if they exist. A real number k satisfying vector AB equals to k times the vector BC. This based on the multiply of vector with real number. And method number 2 use the power of a point with respect to the circle to group collinearity. Here's the theorem 2.1 is the definition of power of a point with respect to a circle, as you can see above. And the constant of the power of point P with respect to the circle O with radius R is equal to the square of PO subtracting the square of R. Next, we have the definition of the radical axis of 2 circles. Let O1 and O2 be 2 circles with different centers, and the radical axis of O1 and O2 is the locus of points whose power with respect to O1 and O2 are equal, which is a straight line and perpendicular to line O1 and O2. Now we consider 2 typical exercises of each method. Problem 1.7 use a vector to prove the collinearity. This is from the Grumani Junior Mathematical Olympiad 2004. On the side of the idea of a rhombus ABC, we get the points EF so that AE is equal to EF. The line BC, DE intersects at P, and line CD, DF intersects at Q, with that P and Q are collinear. In the solution, the idea is that we use the condition from the problem that AE is equal to DF and AC is a rhombus. We denote alpha equal to PE over PD and beta equal to QF over QB. We can easily put that I must be equal to 1. And then by some simple transformation, as we showed above, we can prove that vector BA equals to minus alpha on beta times a vector QA. Since therefore the vector PA and vector QA are collinear and PQA are also collinear, and this completes the proof. Now we consider the problem which uses the power of a point with respect to the circle to prove collinearity. Problem 2.5 from 1995. I am electronics. Suppose that ABCD is a cyclic quadrilateral and let E be the intersection of AC and BD, F be the intersection of AE and CD. Denote by H1 and H2 the outer center of triangle EAD and EBC respectively. We need to prove that FH1 and H2 are collinear. To solve the problem, we should first prove a basic lemma. It is pretty well known. Given a triangle and 2 segments is from different vertical of this triangle, consider the circle with the x diameter, then the outer center of the triangle lies on the vertical axis of the circle.
It is easy to prove it since we have the power of h with respect to 0m and 0n are equal to the product of HA and HA comma. Applying the lemma to the problem, we have H1 and H2 both lie on the radical axis of the circles with diameter AB and CD respectively. Since ABCD is a cyclic quadrilateral and F is the intersection of AB and CD, therefore we have FA multiplied by FB equal to FE multiplied by FB. Therefore F also lies on the radical axis of that circles with diameter AB and CD. Therefore H1 and H2 are parallel. In conclusion, in this research topic we have introduced two new methods to prove the collinearity of glucons, and we hope that our research can be widely used as a great and useful tool for students to prove the collinearity of glucons in a better way. Thank you for listening.
Thank you, Group 11, for your encouraging presentation. And your English is so fluent and well done. Now we would like to invite Group 12. Your presentation is a complicated order of integral and application, presented by Phạm Đức Duẩn, Nguyễn Hải Đăng, Trần Mạnh Đạt, Tạ Hà Nguyễn, supervisors by Master of Science, Hoàng Ngọc Minh. Please welcome to the stage.
Good afternoon, Professor, teacher, friend. Let me introduce myself. My name is Doug, representative of Group 12. To begin, arithmetic is one of this area of mathematics dating back to several thousand years ago. Earlier problems considered were based on notion of counting the elementary concept of arithmetic problems that as in order appeared back earlier hundreds of thousand years ago. Up to this time, arithmetic has changed a lot. Change explored the extent that was a broad conflict. Our team established by Nguyễn Hải Đăng, Trần Mạnh Đạt, Phạm Đức Duẩn, Tạ Hà Nguyên, with the help of the Master of Science, Hoàng Ngọc Minh, we going to one of the complicated order of integer. Then we start by introducing notice relating to the order of integer. For negative positive integer n and positive integer a, we denote by the multiplicative order of integer. A to the smallest positive integer s, that a to the s is congruent 1 to m. And here comes the corollary. If a is raised to the exponent case, it congruent to 1 to m. If and only if s divided case, we now get ready to solve legion of problems. Let's go through this subject and appreciate our need of solving them. That we face first problem. A and B are relatively variable. Denoted by A to the sum, A to the 2 to the n plus B to the 2 to the n. Our task is to prove that every odd divisor of A to B of the form 2 to the n plus 1 times p plus 1. And our solution. Suppose P arbitrary outright factor of A, and if it is T such that Bt is congruent to A module P, that is the order of T module P, and we will know that S is of the form 2 to the n L, where L is less or equal n plus 1. After n equal n plus 1 is proven. Since P minus 1 divided, we will know that P is of the form 2 to the n plus 1 times P plus 1. This completes our solution. Let me move on to the problem 2. Prove that our group we assume to the contrary is raised to the exponent of n plus 1 minus 1 plus 1 is divisible by n. In this case, n minus 1 is a form due to the n has been directly odd integer that be arbitrary prime number n, and you see that is congruent to 1 module due to the n plus 1, and hence it n minus 1 is divisible by 2 to the n plus 1, and finally we will get that this is divisible by 2. Come to our desirable contradiction. This completes the proof. Let's now return to problem 3. For A and B are two relatively bright people greater than 1. P and Q are two odd divisors greater than 1 of A to the 6 to the n, P to the 6 to the n. Find the relator upon the division of P to the 6 to the n plus P to the 6 to the n by 6 times count to the n. Our solution within the number to finish the problem. First, if A is congruent to 1 mod to P to the n, then it follows that A to the P to the n is congruent to 1 mod to P to the n plus n. Now we can back to our problem. Suppose P is also arbitrary prime factor of A to the 6 to the n plus B to the 6 to the n. Applying the problem 1, we will have that R is congruent to 1 mod to the n plus 1. And applying the lemma, we have P to the 6 to the n is congruent to Q to the 6 to the n, and is congruent to 1 mod to the 2n plus 1. Similarly, applying the lemma, we will have P to the 6 to the n incongruent with Q to the 6 to the n, and incongruent with 1 mod P plus to the n plus 1. From 1 and 2, it is easy for us to deduce that P to the 6 to the n plus Q to the 6 to the n incongruent with 1 mod to 6 times count to the n. And finally, I'd like to look at problem 4. File of positive integer A and such that our solution. In case else n is greater or equal to suppose P is a small prime factor of n, and it exists T such that AT is congruent to 1 mod with P, and it follows that P is divided by AT plus T to the exponent of f minus 1. That is the order of AT plus T mod with P, and hence we will deduce that f equal 1. And finally, we get P equal 1. We come to our desirable contradiction. This completes the solution. We've gone through 4 problems and can see that arithmetic is just as beautiful. Many thanks for your attention, and I wish us the most successful seminar.
Thank you very much for your professional project. Good job. And I would like to invite group 13 to present the sum problems on Olympiad Geometry, presented by Phạm Đức Nhật Minh, Phạm Minh Nghĩa, and Nguyễn Ngọc Chi Lan, Trần Quang Huy, supervised by Master of Science Nguyễn Văn Sơn. Please welcome to the stage.
Hello everybody. Today we shall introduce you to our research topic, including how we generate problem and expand idea from geometric problem. This is our report group. Our group consists of Nguyễn Chi Lan, Phạm Đức Nhật Minh, Trần Quang Huy, and me, Phạm Minh Nghĩa, and we want to give a big thanks to our supervisor, Master of Science Nguyễn Văn Sơn. And here is a simple diagram to how we generate new problem from old one. First, from the solution, we get some special properties of some things in the problem, and with some little more creativity, we generate new one. Now, here are two very simple examples. First, let ABCD be a cyclic quadrilateral. Let P, Q, and R be the perpendicular projection of the point B to the line BC, CA, and AB. Prove that PQ is equal to QR if and only if the angle bisector of angle ABC, and the line AC are contrary. Yes, it's a simple diagram. Using a similar triangle pair, we got the following equality, and hence we generate this one, and the problem is easily proved. And here are our idea to the explanation of the problem. First, we got the equality which can express PQ over QR by the sign of the quadrilateral ABCD. And hence, since PQ are collinear by the fixed line theorem, the conclusion PQ is equal to QR can be restated. DQ is median of the triangle DPR, and thus we can make DQ suspension line in triangle DPR. And here's the example. We want it to be the median. Thus we got the following ratio, and it generates the equality which concludes that BD passes through the midpoint of AC. Here we see BD passes through the midpoint of AC, and DQ is the median of triangle DPR. And with the same idea, we generate some more problem. Here we see is that DQ can be the bisector, and DQ can be median. Q can also be the point of channel C, and also we can manipulate PQ over QR to whatever we want. And next, this is a simple but interesting problem. Let ABC be an acute angle and non-adjacent triangle. The circle with diameter BC intersect A, B, and C respectively at N and N. O is the midpoint of BC. The bisector angle BAC and angle NON intersect at R. Prove that the circle triangle BNR and CNR meet at a single common point on BC. Here's the diagram. You can see this is the circle with diameter BC, this O, and here's M and N. It had a very simple proof. Since ON equal to OM, then Rn is equal to Rn, and in the triangle A and N, the angle bisector intersect the opposite perpendicular bisector at R, so A and R must be cyclic, and it is easily proved using the famous Rico theorem. Also, here the idea. We don't have to care about O and the bisector. We only see that the keys, the main keys A, M, R, N is cyclic, and if R lies on the ABC circle, then M, N, and K are collinear. This is the famous one in sensor line. And sum up all those ideas. We generate the problem. Let ABC be a triangle inscribed in its circle, and R is a point on its circle. An arbitrary circle passes through A and R, intersect AB and AC at M and N. Then MN, BC, the circle, BRN and CRN passes through a common point. Here's that point X. But this is too simple. We want to make the more challenging one. We can hide the property of R. let's note that if H is the ortho center of triangle ABC and N is the midpoint of the line of segment BC, BE and CF is the antecedent of triangle ABC, then if N H intersect the circle AF, H, E, R, then R lies on triangle ABC circle. This is a common lemma. And we also got this one. I in the circle in circle of the triangle ABC and DEF in this point of triangle C. AI intersect the circle triangle ABC and J. Then if JE intersect the second circle AEIF again at R. Then R also lies on the second circle ABC. Hence we can make a more challenging problem. And here's and thank you for listening. Here's our report to our research report to how we generate more problems. Thank you for listening and a bit time to Mr. Sir, our supervisor. Thank you.
Thank you, Group 13, for your clearly and brilliant presentation. And now, while waiting for the time for the calling prize, I would like to invite all of the guests of honors, ladies and gentlemen, and boys and girls. We have time to enjoy some performance by the students in our school. Please welcome. Are you eager and excited for the time for calling prize? Yes. Oh, in the groups when we come the winner, the first winner, the second runner, and who will win the first prize in the competition today? We will know in a few minutes. Yeah, while waiting for the time for the performance and calling prizes, we would like you to have some performance again. Songs by teachers Park Hung, please.
Trong lúc đợi kết quả của giải báo cáo học thì tôi xin tặng các em học sinh
một mình và em một mình biết ồn ào em lại chơi anh như con tàu lăn sóng từ hai phía biển một bên và em một bên cho dấu mai đây xa ánh đèn thành phố anh đến muôn ngao đứng thăm thầm anh sao trời anh vẫn thấy đời không lẻ loi biển một bên và em một bên đất nước xa lao chưa bao giờ bình yên cơn bão chưa chân tâm hồn yên có người anh đứng rằng trời khuya đau đớn đêm cho dỗ mai đây thôi không còn biển nguyên, không có em yêu anh chỉ còn với cỏ. Cho dấu đây thì anh vẫn nhớ biển một đêm và em một đêm, biển một đêm và em một đêm.
Master of Science, improvement for your beautiful songs and sweet voice. Now it's time for prize calling. Can you guess who will win the first prize, second prize, and the third prize? To save time, let me to announce the consolidation prize first. I am very pleased to announce that Group 1, 2, and 3, and 7 win the consolidation prize. And I would like to invite Dr. Phạm Văn Quốc and Dr. Lê Công Lợi will come to the stage and work for the students. Now please, the presentation, the presenter. doctors, Nicola and Phạm Văn Quốc. Thank you, group 6 and 11. Please back to the seats, please.